Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Sahib Noor and welcome to another lecture of Electromagnetic Field Theory. This is our lecture number 7 of the course, and we will study topics from chapter number 2. The title name of the chapter is Vector Analysis. Main topics of this lecture are to study a vortex source, which is cause of a curl of a vector field, and we will also discuss a theorem which relate a surface integral with the line integral, and this theorem is called a Stokes theorem, and we will also solve few example to understand this lecture. So let's start our first topic, which is curl of a vector field. But first we will discuss the vortex source, which is cause of a net circulation of a vector field. A source which causes a circulation of a vector field around it is called a vortex source. For example, we have a conductor and in which the current is flowing in either direction. So the one of the effect of the electric current is to establish the magnetic field around the conductor, such that the conductor become the central axis of this field. So the current is a source for establishing the magnetic field, and such a source is known as a vortex source. We have many sources as well which can establish field. For example, if a charge which is at rest in a free space can cause a static electric field, so that charge is also known as a source. But this is not a vortex source because the field is spread in all direction, while due to current, when the charge is flowing in a conductor, the magnetic field is established around the conductor. So the current in this case is known as a vortex source. And then the net circulation of a vector field around a closed path is defined as the line integral of a vector over the path, which means that we can represent the net circulation of a vector field with a line integral, and mathematically it can be written as circulation of a vector A around a closed path is equal to the line integral of that vector, and the symbol on the integration represent that we are integrating the vector field or a closed path. So this closed symbol represent our closed surface, and if this A is equal to force, then the line integral will represent the work done in a closed loop, and if the work done in a closed loop equal to 0, or if the line integral of f dot dl is equal to 0, then the force is said to be conservative, and we can say that the work done is independent on the path. And similarly, if A represent the electric field intensity, then the line integral will represent the electromotive force around a closed path, which is the potential difference. In some case we call it a potential difference or the electromotive force. And again, if E dot dl, the intensity multiplied with the length element equal to 0, then we can say that the field is a conservative field. After defining the net circulation of a vector field of a source around a central axis, we will define the curl of a vector field and will write the mathematical form of a curl. The curl A is a vector whose magnitude is the maximum net circulation of a vector A per unit area, as the area tend to 0, and the direction of the curl is the normal direction of the area when the net circulation is maximum, which means that the curl of A is a vector quantity and can be defined as the maximum net circulation of that vector per unit area, and the direction of the curl of a vector A is the direction of that small surface whose direction is normal to the plane, and can be written as curl of A is equal to del cross A. This represent curl. Del cross A represent the curl. So curl of A, or symbolically del cross A, is equal to the maximum net circulation per unit area, such that the direction of the curl is the normal direction of the area, which tend to 0. And in generalized coordinates, the curl of a vector can be written as in the matrix form. So curl del cross A is equal to 1 divided by the metric coefficients, that is h1, h2, h3, and 3 by 3 determinants, in which the first row will contain the generalized base unit vector along with the metric coefficient. So a u1 h1, au2 h2, au3 h3, and then the second row is for the differential operator del by del u1, del by del u2, del by del u3, and then we have the third row is for the vector whose curl has to be calculated. So our vector is A, whose components are a1, a2, and a3. So this is the generalized form of the curl of a vector A, and we can make them specific for our specific coordinates. Like we have 3 coordinate system, we can find the curl in the Cartesian, in the cylindrical, or in the spherical coordinates. Now in this slide we will discuss a tool which is a very important tool to study the course of electromagnetism, and this is known as the Stokes theorem, which relate the surface integral with the line integral, or converse. A line integral can be converted into surface integral with the help of Stokes theorem. The Stokes theorem is a useful tool which transforms a surface integral of a curl of a vector around an open surface into a line integral of that vector over a closed path, and mathematically it can be written as the surface integral ds represent a surface. So a surface integral of a curl of a vector A can be transformed into a line integral of that vector around a closed path. Here we put a closed ring over the integral, so this represents the closed path, and you will see that this, and on the left hand side we have a surface integral of a curl of a vector A, and this can be transformed into the line integral of the same vector A around a closed path. And if curl A is carried out over a closed path, then the right hand side of the above equation becomes 0. So we can say that the surface integral of a curl of that vector A become also equal to 0, and a curl free vector field is called an irrotational or a conservative field. Now we will study few example related to Stokes theorem and curl of a vector field. In this slide we will verify the Stokes theorem for a quarter circular disk, and the given function which is vary over the circular disk is given as f is equal to ax xy minus ay 2x. So the given function is in the Cartesian coordinate, and the radius of the quarter circular disk is 3, and from the figure it is clear that the circular disk lie in the xy plane, and we have to verify the Stokes theorem for these point A, B and O. So we have to choose a closed path, and the closed path is from A to B and then B to O and then O to A. So this is a closed path, and the angle varies from A to B, which is equal to 90 or pi by 2 radian, and the radius of the disk is given as 3. So in order to verify the Stokes theorem, first we have to calculate the surface integral of a curl of the given function, and then we will calculate the line integral of the given function or a closed path. In order to calculate the surface integral of a curl of a vector field f, we have to choose the surface element from the given figure, as the disk lie in the xy plane, so the plane must be made by x and y component, and the normal of this plane is parallel to the z axis. So our surface element ds becomes as az dx dy, and then we have to calculate the curl of a vector field f. So the curl of a vector field f can be calculated by the determinant method. So in first row we have written the base Cartesian unit vectors, and in the second row we have write the differential operator, partial differential operator, del over del x, del over del y and del over del z, and in the third row we have to write the element of the given function, which is fx, fy and fz. From the given function, fx is equal to xy, fy is equal to minus 2x, and the z component is 0. So after putting the value of fx, fy and fz, we will obtain the curl of a vector field, which is equal to minus az into 2 plus x. Now after solving the curl of vector field f, we can calculate the surface integral of that curl of f, and putting the value of the curl of f and the area element which is parallel to z axis, and we will left with the integral 2 plus x dx dy, as az dot az become 1, and we have to integrate 2x plus 2 plus x with respect to x and y. So this is a double integral equation, and the limit of x and y will be like, if y varies from 0 to 3, then x will varies from 0 to square root of 9 minus y square, and solve the integral with respect to x first, and then puts the limits of x, and the equation will have a single parameter which is y. So first we have to solve this integral with respect to x, and then we have a single parameter y, and then we will use a special integral formula to solve the remaining integral. And for the given disk, the equation of circle is equal to x square plus y square, and the radius of the circular disk is 3. So our equation becomes x square plus y square is equal to 9. And after solving the integral, the double integral, our answer will be minus 9 into 1 plus pi by 2. And this is our left hand side. Now our right hand side contains the line integral of the vector f, and we have to solve this line integral or a closed path. So our closed loop is a, b and then o, and our final point is again a. So we have to make a loop a, b, o and a. This is a closed loop, and the length element is the disk lie in xy plane, so our length element must contain the term of x and y. So our length element becomes ax dx plus ay dy. So first we have to calculate the dot product of f and dl, and the value of f is this, and then we put a dot and then the elements of the length vector, and after calculating the dot product we will have xy dx minus 2x dy, and for this integral can be split into three elements. For first we have to calculate this integral from a to b, and then from b to o, and finally from o to a, so our loop will be completed. And the integral from o to a and b to o is equal to 0, and you can solve it easily. And the integral from a to b is solved in the past lecture, and the value of the line integral from a to b is equal to minus 9 into 1 plus pi by 2. So the answer of the right hand side, which is the line integral of the function f, our closed path, also equal to minus 9 into 1 plus pi by 2. So the Stokes theorem is verified because the surface integral of the curl of vector f is equal to the line integral of the same function over the closed path, and the answer of the right hand side and the left hand side is matched, so we can say that the Stokes theorem is verified. Now in this slide we will discuss an example, and we have to find the curl of a vector A, and we have to show that the del cross A is equal to 0 if A is given like a phi k divided by r in the cylindrical coordinates, where k is a constant term. So in cylindrical coordinates the metric coefficient h1 becomes 1, the metric coefficient h2 becomes r, and the metric coefficient h3 is equal to 1, and we have a generalized formula for the curl of a vector field in u1, u2 and u3, and our problem is related with the cylindrical coordinate, so we will replace u1, u2, u3 with the r phi z. So the curl of vector A in the cylindrical coordinates is equal to 1 divided by r, and then we have to write the first row as ar a phi into r and az, which means that in first row we have write the base unit vector of the cylindrical coordinate along with metric coefficient, and then the second row is for the partial derivative. So our partial derivative will be del over del r, del over del phi and del over del z, and then in the third row we have to write the component of a given vector. So our vector is r, our vector is a, so we have to write the component of vector a in cylindrical coordinate along with metric coefficient. So ar, r a phi and az as h1 and h3 is equal to 1, so we have only az and ar, and h2 is equal to r, so this will multiply with the second component of the vector a in the cylindrical coordinate. After writing the components of a, and we know that the given function a has only 5 components, so ar and az become 0 and a phi is equal to k by r, so here r is present, so r will cancel with r and we will left only with k. After calculating this determinant we will have 0, which show that the curl of a vector A is equal to 0 in the cylindrical coordinates. Another example is also related with the curl of a vector field A. So we have again show that curl of A is equal to 0 if A is given in the spherical coordinate, and A depends upon the radial component only, and the spherical coordinates are r, phi, z, and fr is any function of the radial distance r, which means that this may be a function or combination of a factor which involve only a radial term. And we know that in the spherical coordinates we have h1 is equal to 1, h2 is equal to r, and h3 is equal to r sine theta, which are the metric coefficient, and the generalized coordinate u1, u2 and u3 will replaces by r theta phi. This is the radial component, this is the half angle which vary from 0 to pi for any sphere, and this is the plane angle which vary from 0 to 2 pi, and thus the curl of a vector field A in the spherical coordinate becomes 1 divided by r square sine theta into ar a theta into r and a phi r sine theta. So as we know that the first row of the determinant will be for the base unit vectors along with metric coefficient, and the second row is for the partial differential operator del over del r, del over del theta, del over del phi, and in the third row we have to write the element of the given function a and along with metric coefficient. After putting the value of a, and we have only a radial component, as we have ar, fr, and our a phi and a theta term equals to 0, and we have only a radial component of the function or radial component of a vector. After calculating the determinant of this vector a, we will have equal to 0. So the curl of vector a in the spherical coordinate which has only a radial component become 0. From these two examples we can conclude that the curl free vector field is called an irrotational or a conservative field, and we will see in next chapter that electrostatic field is an irrotational or a conservative field. So let's summarize over this lecture. In this lecture we have discussed the curl of a vector field, and we have also discussed the cause of a curl of a vector field, and which is a source, and that source is called a vortex source. After discussing the curl of a vector field, we have also discussed the Stokes theorem, a theorem which convert a surface integral into a line integral or vice versa. At the final stage of this lecture, we have discussed two problems which are curl free. If a function is only related along the radial line, so the curl of that function will be always equal to 0, and in next chapter we will discuss that the curl of electrostatic field is always equal to 0. Our next lecture will be about few identities called the null identities. Along with these identities we will also study a theorem which is known as the Helmholtz theorem, which contain the divergence and the curl part of a same function. And if you have any question and any difficulties related to this lecture, you can contact me at my email and I will reply as soon as possible. Thanks and Allah Hafiz.